All right, today we're going to compute the extrema of three-dimensional surfaces.
What?
We're going to compute extrema of three-dimensional surfaces.
Yeah.
Anyway, why don't we do one of them? I'll do one of the 6 problems. Yeah, let's just do one of them, then you only got 5. Okay, so this is what we're going to do to figure out whether a stationary point. Did we already discuss stationary points?
Yes.
I think they used it in your book last year. A stationary point, okay, in 2 dimensions. In 2 dimensions, a stationary point, okay, let me give you something. Oh, a stationary point is when the derivative is equal to 0. How does that differ than a critical point? Come on, you guys all had 5s on the AP exam, right? A critical point is when the derivative is either 0 or does not exist. That's something totally different. Does not exist does not mean undefined. Okay, so like for example here, see? The slope is 0, 0, and 0. So these are what we call stationary points. So a stationary point is just when the derivative is 0. But in 3 or higher dimensions, what do? We're going to look at the gradient, which tells you the perpendicular vector of the tangent plane, right?
Yes.
Okay, so, and again, just like over here, just because the derivative is 0, does that guarantee an extreme point? No, because, okay, well, that one would be a local maximum, this one would be a local minimum, this is neither, right? So just because the derivative is 0, that doesn't mean you automatically have a maximum or minimum point. And then we have to examine it, right? So if the derivative changes from positive to negative, come on, then it's a relative maximum. If the derivative changes from negative to positive, then you have a local minimum. And if the derivative does not change sign, then you have neither, right? Come on, you guys all had 5s. And you're BC. Even my AB students can do this. Oh my goodness. Okay, but in 3 dimensions, we're going to look at the gradient. So a stationary point is when the x component and the y component of the gradient is 0. Why is that? Think about it. If you have the gradient and the x and the y components are 0, what does that mean? Doesn't that mean the tangent plane is horizontal or parallel to the xy plane? So for example, if you have like something that looks like this, at the highest point here, the tangent plane would be parallel to the xy plane. So that means the gradient, the x and y components would be 0, right? Perpendicular vector. So those are how we're going to find our stationary points. Now once we locate a stationary point, how do you determine if it's a max, a min, or a saddle point? This is where we're going to have to roll up our sleeves and do some algebra. So here, let me erase this picture, let me get a better one in here. Okay, so let's go with a maximum. So let's say we have a stationary point. So we'll say this is f of x, y. Okay? So what we're going to do is we're going to compare that to a point that's nearby. So here's a point nearby. This would be f of x plus h, y plus k. Do you guys understand what that is? That means from this point, you move a little bit either to the left or to the right in the x direction, then move a little bit to the, here, if we're looking onto the xy plane, here's the point. So you can go a little bit left or right, or a little bit up or down. But it's going to be on the surface, so you're going to get the z coordinate there. And then we're going to compare them. So what we're going to do is we're going to subtract. We're going to go f of x plus h, what am I doing? Y plus k minus f of xy. We're going to subtract this quantity, So what do these things give you? This one is the z coordinate of this point. This one is the z coordinate at that point. So if this is going to be a relative maximum, then what should this quantity come out to?
0.
No. If it were 0, then wouldn't they lie on the same plane like this? Look at the picture. This is the z coordinate of this. This is the z coordinate of that. If I subtract, are you going to get like a positive or a negative number? Well, this one is lower than that one, right? So if you go this minus this, you're going to get a negative number. So if this always comes out negative, and that's key now, always, no matter how far you are, h, or to the left or right, or k, up or down, if it always comes out negative, then we're going to have a local maximum. If this quantity is always positive, then you can probably guess. So what happens when you go this minus this and it always comes out positive? Doesn't that mean this point is always going to be below that one? Then we have a local minimum. And then if this quantity is sometimes positive and sometimes negative, then we get a saddle point. And do we know what a saddle point is? Remember on the hyperbolic paraboloid? It's a point that's neither a maximum or a minimum, it's both. So sometimes we call that a mini-max. A saddle point. I can't even draw it. Yeah.
Why does it always have to be like, what if like they're not like min, but it's just that like those 2 points are there, but there's another point on the like below?
Say that again?
No, I understand what you're saying.
I don't know.
So like what if those 2 points are not like,
You mean these 2 points here?
yeah, what if it's not max or min? It's just like on the.
Well, that's why if it's sometimes positive, sometimes negative, then it's going to be a saddle point. Remember the saddle point here? Look at the picture of this hyperbolic paraboloid. This is called a saddle point. It's both a maximum and a minimum, right? Depending on how you look, right? So if you look at it this way, it's a maximum, but if you look at it this way, it's a minimum.
No, what if it's in the middle of the graph? Like 2 points are not.
But then it wouldn't be a stationary point, because then the x and y components of the gradient wouldn't be 0. So the first condition is the x and the y components of the gradient have to be 0.
Oh.
Although, right? Because that's where you're going to have a possible maximum or minimum.
For both
And then-
points?
This is only one point, and then this is a point that's a little bit farther away. In the vicinity, though. Just like, okay, last year, okay, let's go back to calculus 1.
Oh wait, are you trying to only determine what x comma y is?
Yeah, is it a maximum or a minimum?
Wait.
Yeah, we want to know, is this point a max, min, or
I
neither?
thought you were also trying to, okay.
No, we just have to examine points nearby, yeah.
If you can change x and y to like anything and it'll always be lower than f with x and y, wouldn't that mean it's like an absolute max?
No, because this is only nearby.
How do you know if it's only?
H and K are, you gotta consider them tiny positive numbers.
I consider them.
It's nearby. I guess it could be negative. You can't think of X, or I mean H and K as like can be really large. It's kind of smallish in the neighborhood of this point. It's just like, okay, how did you define a local? Okay, let's say you have a graph that looks like this. Why is this a local minimum? Because compared to points nearby, it's the lowest point, right? Why is this a local maximum? Because compared to points nearby, it's the highest point. So same thing here, in 3 dimensions, why would this be a local maximum? Because compared to points nearby, it's the highest point. Nearby.
I don't know if it's nearby. Wait, so.
Well, last year, how did you define nearby?
Because.
Close.
We did like the number line and it's like the minus plus minus. So H and K is not a real number?
Yes, they're real numbers.
What?
Small real numbers. Small real numbers.
But you
Let me
said,
give you an example, 0.1. Negative 0.2.
Mr. Park, you said the condition has to be, the gradient has to be just like pointing on the Z coordinate.
Yeah, it only has a z component. The x and y components have to be zero.
Component doesn't.
Were you here? Look, when you have a maximum point like this, if you make the
Yeah, I was
tangent
looking for that
plane,
word.
if the tangent plane is going to be parallel to the xy plane, then doesn't the normal vector have to point either straight up or straight down? Which means the x and the y components of the gradient got to be zero. We've never talked this much about it before. We can explain this in like 1 minute. Well, not this year apparently. Okay, can we move on to doing an actual problem?
Yes.
Okay, I'll leave part of that on the board. Okay, let's pick one. The first one is really easy. Now, the hardest part is you gotta do the algebra, and then you gotta look at the quantity, and you gotta figure out, is it always positive, always negative, or sometimes positive, sometimes negative? Okay, I wanna pick one that's gonna come out to something that's unusual. Okay, let's try D. I have no idea if this is, but if not, then I'll tell you what to look for in tonight's homework. So we got Z is equal to x cubed. Can somebody read it to me?
Minus 3x plus y.
Plus y.
Got it right there?
Yes.
Oh, that's weak. We'll just do it then. Okay, so how do we compute gradient? Normally, what do? We go f equals x cubed minus 3x plus y minus z, right? But if you think about it, we're not even looking at the z component anyway, but that's okay, we'll just do it. So what's the gradient? X component, partial with respect to x.
3x squared minus
Partial with respect to y.
1.
Okay, this is weak, this problem. This is really weak, this problem. You know what, I don't want to do it. No, it's too easy. I want to do something that's going to come out to like something where you got to think, that's why. Okay, E. Okay, somebody read that to me. Z equals,
x squared plus xy plus y squared minus 3x minus 3y.
okay, even that looks kind of weak. Don't worry, I'm saving up the good ones for the test. Oh. Okay, so gradient, we go f equals x squared plus xy plus y squared minus 3x minus 3y minus z. So the gradient would be partial with respect to x. 2x plus y minus 3. Okay, now at least that we can work with something here. Partial with respect to y.
X plus
Partial with respect to z.
minus 1.
And can you see, look, if it's always z equals, you're always going to get a minus 1 over here, right? But we're not even looking at that anyway. So all that matters is the partial with respect to x got to be 0. And then the partial with respect to y also has to be 0. So you could actually just look at this and take the partials of x and y if you want. You don't really even have to make the gradient because you're not even looking at that. Okay, so that means 2x plus y minus 3 got to equal 0. And 2x plus 2y minus 3 equals 0. And then you need to solve these equations to get the stationary point. Okay, so what do you suggest here?
Plus y. Plus negative 2x plus 3 and
Substitution, addition,
Times it
subtraction.
by 2 and then subtract
Yeah.
the equation.
So say that again.
Do the thing.
What thing?
The Josh said.
Substitution.
No, the other thing. The,
Elimination.
yeah.
All right. So keep this equation, 2x plus y equals 3. And then somebody said multiply this equation by 2 or divide it by 2. Either way, right? It doesn't matter. Okay, multiply it by 2. 2x plus 4y equals 6. Did I do that correctly?
Yeah.
And then subtract, except when I subtract, why don't we go this minus this, that way we get positive numbers, right? So this minus this, 3y equal 3, therefore y equal 1. Okay, plug it back into one of these. Which one looks easy to plug into? This one right here?
X equals 1.
Okay, so if I plug in 1 for y, you get 2x is equal to 2, which is x equals 1. See, even this is weak. Don't worry, I'm saving the good trig ones for the test. Yeah. So you can have trig here. See, like over here, no more trig.
How do you have trig?
Sine and cosine. Don't worry.
Come on.
Okay, so the point f of 1, 1. Actually, we can call that point 1, 1. How do you figure out what the z coordinate is? Plug it back into here. So there's only one stationary point. Okay. I like the problems where you could get like 3, 4, or 5 stationary points. Those are good. Anyway, if you plug in 1 for x and 1 for y, what do you get? 1 plus 1 plus 1 minus 3 minus 3. Negative 3. So is this point a local maximum, a local minimum, or neither?
Oh, wait, what?
You have to. Are you serious? Were you here 5 minutes ago? We have to examine this quantity. Okay, let's review again since I erased it. If this quantity is always positive, then this point is a local minimum. If this quantity is always negative, then this would be a local maximum. And if this quantity is sometimes positive, sometimes negative, then we have a saddle point.
Yeah, I meant like, how do you know it's
Ancient, they're small values.
So do you just plug it
Because
in?
you gotta be in the nearby, in the region.
Are you gonna? Okay,
Do I have to draw a picture from last year again? Wait, no, I'm
Oh,
good.
you
No,
saw
too late, I gotta do it.
it.
Why do we call that point a local minimum? Because when you compare it to points nearby, it's the lowest point. It might not be the lowest point on the entire graph. If it were, we would call that the absolute minimum. But if it's the lowest point compared to points nearby, then it's a local minimum. So that's what H and K.
Oh! Oh, Z is F1, 1 is Z. Oh, that makes sense.
That's the picture I drew. Remember the picture I drew comparing the Z coordinates?
That makes sense. Okay, I see it. I know how to do it now.
Okay, wait, before we even move on, where did the 1 and 1 come from, Mr. Park? Where did the 1 and 1 come from?
Solve X equals
That's the
1.
stationary point.
Oh, okay.
That's when both the x and the y components are 0, which means the tangent plane is parallel to the xy plane. That's a possible maximum or minimum point. Okay, now, you gotta do the algebra. You just gotta crank it out. Okay, let's do the first one. Let's see if we can squeeze it in here. Okay, f of 1 plus h, 1 plus k. So here's the original function right here. Don't look at this, look at this, yeah? This f is different, yeah? So just look at this one, z is like f. Okay, plug in 1 plus h for x and 1 plus k for y, go.
1 plus H
1 plus h squared
1
plus 1 plus h times 1 plus k plus 1 plus k squared minus 3 times 1 plus h minus 3 times 1 plus k minus f of 1, 1, but didn't we already compute that to be negative 3?
plus
Okay, now simplify this. So what we need to do is multiply it out, but come on, it's just
Wow.
algebra. Okay, just tell me if I make a mistake here. Did I do that correctly? Okay, now something should cancel out. Like this 3 will cancel that 3. 1 plus 1 plus 1 cancels that, negative 3.
2H and
Uh,
H.
what?
2H and H cancel the negative
Yeah,
2H and H cancel the negative 3H.
that's okay.
And K and 2K cancel the negative 3K. And oh, see, we picked a good one. H squared. Whoever chose this problem, you chose wisely. Okay, so this is what we get. So is this quantity, now sometimes it's really obvious, like sometimes it might come out to something like this. Isn't this always positive?
Yes.
Right, because whenever you square a quantity, you're not gonna get negative, right? And remember, H and K are non-zero numbers in the neighborhood, yeah? And then if you have something like this, then that's always negative. But this quantity, anybody? Anybody wanna weigh in? Always positive, always negative? Well, we can forget about always negative, right? Or sometimes positive, sometimes negative.
Sometimes positive,
Always.
sometimes
Okay, give me an example of where it would be negative then. What numbers could I plug in for H and K to make it come out negative?
One.
1 and,
You can't.
well, just because you can, how can we guarantee that it's always positive?
This, no.
Okay, there are certain quantities that come up often when you do this analysis here. This is one of them, another one is this one. Like that. Now, of course, if it was 2K, that's obvious, right? Because that's H minus K quantity squared, that's always positive, right?
Oh, yeah.
Okay, but it doesn't have the 2 there. So how do we do it? Well, we'll do it the cheat way. We can use, are you guys good at solving inequalities?
No.
Okay, so I'm gonna do this the baby way then. Why not graph this? Graph this on a 3-dimensional grapher. If it's always above the XY plane, then it's always positive, right? Just like, okay, 2 dimensions. If you graph this parabola like this, isn't it always above the x-axis, so it's always positive, right?
Yes.
So, in 3 dimensions, if this graph is always above the xy plane, then it's always positive, right? Z is always positive then. Okay, so why do we graph it?
You can't do it on the test, right?
No, that's why you gotta know, you gotta keep these in your memory bank. All right, so I have the GeoGebra 3D calculator, so let's punch in x, I'm trying to concentrate here, squared, plus x times y, plus y squared.
You did not know.
So the only time it actually touches the xy plane is when x and y are 0, right? But remember, x and y have to be small positive or negative numbers, not 0. You know what I'm talking about?
Yes.
Okay, and then what if we change this plus sign here? Can I edit? Change it to a minus sign. How does that affect the graph?
Makes it,
It
it turned, no.
didn't really affect it that much, yeah? So anyway, so those of you watching on video, all we did is we graphed it. So we can say that when H and K are small numbers, both of these will always be positive. So therefore, this point here is
Local
it's always positive.
min.
Local minimum. And that's how you figure out if a point in 3 dimensions is a local max, local min, or saddle point. Of course, quantities that are sometimes positive, sometimes negative would be something like this, right?
H squared minus.
Like that. Because if H is positive and K is positive, then it's positive, but what if H is positive and K is negative?
Yeah.
Yeah, so, don't worry, I'm not gonna give you something like out of the blue, but you also have to be able to do work with trigonometric functions as well.
What if it's like H squared plus 10 HK plus K squared?
Okay, say that again.
Just adding the 10 plus
H squared
plus 10 HK. that without graphing actually.
Don't give you ideas.
I'm thinking it's, sometimes positive, sometimes negative.
I think so.
That's what I'm thinking. Well, let's try graph it and see. I mean, that's just a feeling I have, but I don't know. Okay, so let's put a 10 in the front. Edit.
K is negative 2.
Isn't it
And H is
Sometimes
1, that's
it's-
negative.
kind of
Do I have to put a time sign there? So is that the graph?
Whoa.
Oh yeah, now you can see, yeah, look. So the graph does go below the XY plane, doesn't it?
Yeah.
Yeah. So it's sometimes positive, sometimes negative. I don't know, this is what I was feeling.
Yeah. I'm putting 1 and minus 1.
It's like,
A 1 and negative 0 is all.
1 and minus 1.
I mean, dude, that one, it's like, you can move the HK to the other side and then add 2HK, and then like, show a contradiction.
What? Look, you're looking at this one.
Yeah,
Okay, so what?
like, you move, or just add an HK to both sides, so you get H plus K,
Squared.
H plus K squared is greater than HK. And then like, assume that like, that thing is less than 0.
Which one? The HK.
Yeah. Or no, H squared plus HK, like, do a proof by contradiction and assume that that's like less than 0. And then subtract 3HK from both sides,
From this?
from the original one. And
From
then
this
like,
one?
you'll get like, HK should be like greater than 0 and HK should be less than 0, and then it's a contradiction. But then like, if you had 10HK, then like, to get it to the H plus K squared form, you would subtract 8HK, so then it would be a negative, so you can't get a contradiction.
I'm lost.
Yeah, I'm not following that either. This is what I was thinking. Like, if K was 1 or some positive constant, I guess it would be easier if it's 1, then the discriminant would be negative. Right? So doesn't that mean the graph is either always above or below? Right, just like in 2 dimensions, if the discriminant, here, something like this, x squared plus x plus 1. Since the discriminant is always negative, that means the graph is not going to touch the x-axis. So it's either going to be always above or always below, right? So you just test one point, like this point here is 0, 1, it's above.
All
It's positive, so it's always going to be positive. So I was kind of thinking the same thing for this, but I'm not really skilled at solving these types of inequalities.
So, from 3HK, it's most likely gonna be sometimes negative, sometimes positive. This 2 makes it 0 for the derivative, which.
Yeah, that's what I'm thinking. So if this coefficient here is bigger than 2, then it's going to be sometimes positive, sometimes negative. Now, why would that be? Well, look, then you could complete the square then, yeah?
Or if it's bigger than 2, you can always plug in 1 and minus 1.
Like if this were 3, then couldn't you go h squared plus 2hk plus k squared and then minus hk,
Plus
right? So that would be h plus k squared minus hk.
plus
Huh?
HK.
What?
Because 3 HK.
Oh yeah, plus. Plus. Okay, but how do you how would you guarantee that sometimes positive, sometimes
You
negative?
always plug in 1 minus 1.
So just plug in numbers again then.
Yes.
No, but if you plug in 1 minus 1, like, for any, if the HK term is greater than 2, then
I mean, yeah, that makes sense.
That makes sense.
Because H and K will be always one, so the middle part of the pages will be less than 2.
We should actually look this up for a mathematical proof.
He's done.
Well, he's doing the reductio ad absurdum, proof by contradiction.
What is
Here,
it?
look it up on your iPad.
So like
Prove,
it's like
here, just type in, prove,
Greater than 0 and less than.
proof.
So this is.
X squared plus xy plus y squared is always greater than 0. Try type that in onto your,
Yeah, and then you, like when you subtract it off, then like this will be negative, so like you can't get a contradiction out of it.
oh, they do it by contradiction also. Whoa, Mark.
Math statistics.
Okay, can we look for a proof that's not by proof by contradiction?
not because
Wait, should I just think
Here, another proof. Physics forum. So they complete the square. Not sure where to go from there. Alrighty then. Okay, anyway, I'm just telling you now, these quantities are gonna come up, so just put it in your memory banks. They're always positive. Okay, so right now there's no shortcut, but remember last year we learned another way to, in 2 dimensions, how do you determine whether a point is a local max or local min? What did we do last year? We did the first derivative test, right? We make the number line. So if the derivative changes from positive to negative, it's a local max. If the derivative changes from negative to positive, it's a local min, right? If it doesn't change sign, it's neither. But was there another test that we did? The second derivative test. Remember what that was? If the first derivative is 0 and the second derivative is negative, which means the graph is concave down, then that would be a local maximum, right? If the first derivative is 0, but the second derivative was positive, which means the graph is concave up, then you would have a local minimum, right? That's the second derivative test. Do you think we might have something like that in 3 dimensions? And the answer is yes, but we'll learn that tomorrow.
Are we done?
Yeah.
Oh.
So I did one of the problems for you, so you only got 5 problems for homework. Also, we found the proof.
oh, it's proof by contradiction though. Like,
That's right. I want a proof that's not by contradiction. Or maybe that's the way that you have to do it, yeah?
yeah.
Oh, speaking of proofs, do you know when we finish multivariable calculus, we're going to study proofs?
Wait. If
We actually used to do this in PCH, but
if we
they got
finish
taken out over the years.
Are we done?
Say that again?
Oh.
Well, say that again?
Wait.
Oh, no, hold on, I want to hear what you said.
I thought you said like we're gonna meet up in second semester and do proofs.
No, we're going to finish multivariable before the first semester's over.
She was expressing her passion for math.
Anyway, is this course a year course or a semester course?
Semester.
Are you sure?
Yes?
Are you sure?
Yeah, I have a class period 8 second semester, so it's like,
Our Bible.
I have EPF. So what did he say?
Really?
Yeah.
I thought it was a year class.
No. Yeah, I had Bible second semester.
Wait,
During period
Bible.
is this me? I can switch back.
No.
I can switch back.
Okay, it doesn't matter. I just
drop EPF.
thought it was a year course.
Wait, what?
You can't
Josh,
switch-
what do you
you
have?
need
I have econ period 8, but I have a period 6, so I'm basically.
Oh.